Hey everyone, and welcome to today's Explainer. We're diving into some seriously fascinating source material today that outlines a massive, really game-changing paradigm shift in motor and capacitor bank monitoring. Specifically, we're talking about operational monitoring. The core argument here is that we need to completely move away from guesswork and rigid service schedules and instead embrace data-driven equipment health based on actual operational duty. Think about your car for a second. Traditional calendar-based maintenance is a lot like that little oil change sticker on your windshield. You know, the one that tells you to come back in exactly 6 months, regardless of whether you drove 500 miles or 50,000. It's just a rigid guess. On the flip side, runtime-based maintenance acts like your car's actual odometer. It triggers a service alert exactly when a specific operational duty threshold is crossed. It just makes so much more sense, right? So here is our roadmap for today. We're going to cover 1. The flaw of calendar maintenance. 2. MDSOPT, the unstoppable stopwatch. 3. Thermal memory and RTDs. 4. SSCBR, breaker health checkup. 5. The flight data recorder. And we'll wrap up with 6. The predictive maintenance advantage. All right, jumping right into section 1, the flaw of calendar maintenance, where we look at how you might be wasting money or completely missing wear. Let's actually make this real with a quick scenario. Picture this. You've got two identical motors in the exact same plant. They are both theoretically due for an every 4,000 hours service. But here's the catch. Motor A has only been running during peak demand and shows 3,200 actual hours. Motor B, on the other hand, is a continuous base load motor and has hit 4,100 hours. So ask yourself, which one actually needs your technician's time right now? If you said motor B, you hit the nail on the head. Motor B needs immediate service, while motor A still has 800 hours of perfectly good runway left. Without tracking actual runtime, both of these motors would probably be serviced on the exact same arbitrary calendar date. That means you'd be dangerously delaying maintenance on motor B while literally throwing away money servicing motor A way too early.
Which brings us nicely to section 2, MDSOPT. Basically the unstoppable stopwatch for tracking real operational duty.
The source introduces this incredible tool called MDSOP. In plain language, it's a runtime counter function block. It's essentially a stopwatch embedded right in the relay that never stops counting while the equipment is energized and running. This gives maintenance planners a true equipment-specific number to track the real duty cycle. Now, a quick warning here from the documentation. You shouldn't rely on runtime hours alone if the equipment experiences frequent starts and stops. Why? Because those starting cycles impose their own separate mechanical and thermal stress that a simple runtime counter just won't capture. But what's really wild here is the sheer precision of this tool. The MDSOPT motor runtime measurement operates with an accuracy of plus or minus 0.5%. That gives operators absolute confidence in the data. You aren't just guessing anymore. You are operating on highly precise, mathematically sound facts. Let's move on to section 3, thermal memory and RTDs, because we absolutely have to track cumulative stress. You see, operational monitoring isn't just about the time the clock has been ticking. It's also about the physical stress the equipment endures. And specifically, we're talking about heat. The source introduces something called T2PTTR. This is a thermal overload model that uses 2 time constants. So instead of just looking at an instant exertion, it tracks winding heat accumulation over time. Think of it kind of like an athlete's heart rate recovery monitor. It remembers the heat buildup and the cooldown periods. It can even take in real-time temperature data from physical RTD sensors, measuring ambient and oil temps to dynamically adjust its protection curve based on actual cooling conditions. The really crucial point here is understanding the difference between these two approaches. Simple overcurrent protection only cares about an instantaneous spike in current, but thermal protection, it tracks cumulative energy over time. And why does this matter so much? Because every sustained 6 to 8 degrees Celsius increase above a transformer's rated hotspot temperature can roughly halve its expected insulation life. Have it. So thermal memory isn't just about immediate survival, it protects the actual lifespan of your asset. Okay, on to section 4, SSCBR. It's time for a breaker health checkup with predictive mechanical monitoring. Enter SSBCR. The documentation highlights the circuit breaker condition monitoring function as an absolute vital safety net. We've talked a lot about motors and transformers, but we also have to consider the mechanical health of the circuit breakers themselves. Standard breaker failure protection is totally reactive, but SSBCR is completely proactive. It tracks key performance indicators to predict mechanical failure and catch degradation long before catastrophic failure scenario ever gets the chance to occur.
Think of these KPIs as your breaker's dashboard. Tracking spring charging time tells you right away if the energy storage mechanism is starting to degrade. Tracking SF6 gas pressure is critical for safely quenching an arc. Monitoring travel time helps you catch mechanical friction, but pay special attention to inactivity time. Seriously, a breaker sitting completely idle for months is a massive risk factor because lubricants dry out and sticky mechanisms develop from pure disuse.
And the most important takeaway from this whole section, track the gradual drift. Do not just wait for a hard alarm to go off. If your spring charging time slowly creeps up 15% over a 6-month period, that is a glaring maintenance signal. It's worth investigating immediately, well before it hits that hard failure limit.
Let's dive into Section 5, the Flight Data Recorder. This is all about logging the system's history.
So with all this incredibly precise monitoring happening, the relay actually functions like the electrical system's own flight data recorder. It runs 4 continuous independent memory banks. First, you have your sequence of events, which logs a running diary with millisecond timestamps. Then you have fault records, capturing snapshots of the latest faults. Next is the disturbance recorder, which captures actual waveforms in ComTrade format for cross-vendor analysis. And finally, the audit trail keeps track of all security-related events and logins. Let's just talk about how this builds your troubleshooting power. That sequence of events log alone can store up to 1,024 process events. That is a massive historical runway for your engineers. It ensures that when something does go wrong, you have an incredibly detailed, time-stamped map of exactly how the system got to that state. And finally, Section 6, the predictive maintenance advantage. This is where we actually put all this amazing data to work. The local LHMI, or LHMI, brilliantly combines a real-time graphical single-line diagram with direct access to that massive event log we just talked about. This means your technician has a complete on-site troubleshooting toolkit right there on the panel. They can see the visual status of breakers instantly and correlate it directly to the exact history. And the best part? They can do the whole shebang without even needing to plug in a laptop. Now, thinking about operations practically, we obviously have to consider access. So here's a quick knowledge check for you. If a maintenance tech needs to check those event logs on the LHMI, but absolutely should not be allowed to alter any relay settings or issue commands, what cybersecurity role should they be assigned in the system? The answer is the viewer role. By following the principle of least privilege, assigning them the viewer role gives them the exact data access they need to read those logs and statuses, while perfectly securing the system's operational integrity from any accidental changes. Which brings us to the end of today's explainer. I really want to leave you with this final provocative thought. Are you still guessing your maintenance dates with an arbitrary wall calendar? Or are you ready to actually listen to what your equipment's actual data is telling you? Once you embrace duty cycle-based operational monitoring, I guarantee you'll never look at a maintenance schedule the same way again. Thanks so much for joining me on this deep dive today. I hope you're leaving empowered and ready to put these tools to work.